Hello, everyone. Welcome to Building Planets Lecture 5. This one is Early Earth, Ready for Life. So first, a recap of the last lecture. Hang on a minute. There we go. Which was about the formation of the moon. And we looked at everything from about 4.5, which is approximately when we think the moon forming impact was, up to 3.8 billion years ago, which is just past the late Hadean bombardment. So the story went like this. The moon started as a molten ball coalescing out of the splash from a giant impact with the Earth, as first shown by the compositions analyzed in this dish of lunar soil brought back by the first Apollo mission, which allowed us to determine the way the moon solidified with the floating anorthosite lid and the magma ocean underneath. From about the time of its solidification until about 2 billion years ago, the moon had volcanoes that produced not just the big lava flows that you see, the dark areas with your eye, but also volcanoes that created these little glass beads like this one in the soils. And between about 3.9 and 3.8 billion years ago, all the rocky planets experienced the late heavy bombardment, and it was these impacts that made the giant impact basins that we see on the moon that were filled then with what are called the Mare basalts. So here's the timeline for today's lecture. It's actually the same timeline. We're going to talk about what was happening on the Earth over the same time period that we covered last lecture for the moon. People used to think that the Earth was hot and uninhabitable for a long time after formation. In fact, the geologic eon up to 4 billion years ago is called, for that reason, the Hadean, or the hell-like. So it stands to reason, right? You would think, but it's one more place where our human intuition turns out to be wrong. And when we look at the data, the chemistry, and the physics, it turns out our intuition is wrong. So what can the steps that the Earth progressed through after the giant moon forming impact have been? And how soon do we think it was cool and comfortable? And what is the evidence left that we can find for that? Well, recall this image from the Magma Ocean lecture. It's an artist's interpretation of a planet just after an impact the size of the moon forming impact on Earth. The idea of that magma ocean was born in 1970 when the first samples were returned from the moon, and the only reasonable explanation for their strange compositions was that they'd crystallized from a vast volume of magma. Though this idea was resisted for some time, it's now pretty clear that the last giant accretionary impact melted the Earth as well as creating a molten moon from the detritus. So what happened next? For the solidification of the Earth, we appeal to models and also to some evidence from the Earth's rocks. In the Magma Ocean lecture, I talked a bit about how the solidification of the magma ocean produced a thick early atmosphere. Here, in this slide, I'm going to talk about the planetary interior. Here's some output from one of our models for the Earth magma ocean. It's very similar to what others have done as well. On the vertical axis here is the radius of the Earth from the core mantle boundary up to the surface. And on the horizontal axis is the density of the solids that crystallized from the magma ocean. So start by looking at the paler before overturn curve. This model uses fractional solidification that I talked about last lecture. That is the idea that one layer of crystals at a time formed and sank and was deposited on the bottom of the magma ocean. And the magma ocean's liquids would then evolve because of the crystal composition that was just removed. And then the next layer of crystals would form and the magma ocean liquids would evolve further. Solidification probably started at the bottom on the Earth, just like for the moon. The crystals became more and more iron-rich as solidification continued, and they therefore became more dense. That's partly why the curve is bending over to the right, that before overturn curve. Some minerals are also naturally more dense, which you can see up here where that mineral sticking out to the right where they're more dense. And also they're also getting colder as they get near the surface, which also makes them more dense. So for many reasons, in summary, when the magma ocean solidified, it is gravitationally unstable with the densest materials at the top. These dense materials sink down because of gravity. They sink and move slowly in the solid state, not liquid solid. Warm solid rock under pressure can flow like liquid over enough time. And we think this overturning event, where the densest cumulates, they're called, the densest mantle materials up near the surface, sank down into the bottom and the lighter ones rose up to the top. It took perhaps 10 million years to be pretty much complete. And when that overturning finished, the density profile would have looked like the second line, the after overturn line, the darker line, with a very dense, deep layer that is probably there today, never remixed by the thermal convection that came after this event. We know from seismic evidence that there is a deep, dense layer with appropriate volume and appropriate density, and perhaps this is how it formed. So then in just about 15 million years after the moon forming impact, the Earth has solidified, and its mantle, that is all the rock between the core and the crust, is stably layered and unmoving. Gradually, over tens of millions of years that follow, that stable mantle would begin to convect, that is to move as a fluid even though it's solid, in response to heat transferring from below and out into space above. Today, almost all of the mantle participates in thermal convection on the Earth, which aids in plate tectonics and produces volcanoes, and it's a key aspect of Earth's heat engine today. But of course, people's assumptions for a long time were that the Hadean mantle would be practically boiling with convection. And now we know it was almost certainly completely still, held still by compositional density layers. So here's the image of, on the left, of the Hadean from Life magazine in 1952. Look at that picture from Life. You see the moon really up close. Recall that the moon formed only about 6 Earth radii away, and now it's over 60 Earth radii away. So back in the Hadean, it would have been quite close by. And people imagined that the whole surface of the Earth would just be boiling with volcanoes and the mantle would be convecting like mad. But then on the right, in 2008, here's a picture from the New York Times of the Hadean, meant to be cool and clement. And so now this is what we think. Models say that the magma ocean is solid in a few million years, and then the planet cooled to clement conditions, that is liquid water on the surface, over just tens of millions of years, so very quickly. One note is the atmosphere probably consisted of carbon dioxide, nitrogen, and some methane and hydrogen, but virtually no oxygen. Carbon monoxide and methane are destabilized. Some people have thought, I'm mentioning this because some people have thought the early Earth's atmosphere would have carbon monoxide and methane, destabilized by both volcanic eruptions, oxygenating them a little bit, and also by solar photolysis, that is breakdown at the top of the atmosphere. So the earliest Earth's atmosphere was probably largely carbon dioxide and nitrogen. These greenhouse gases helped keep the Earth warm while the sun was getting going. Solar heating was less in the early solar system. So the surface may have been mainly cool and clement, but it was not habitable for the likes of us. The rise of oxygen is a different matter. Oxygen is highly reactive, and it was poisonous to the life that existed early on Earth. We won't talk about oxygen at all in this lecture. It comes along a little later in Earth history. So far, I've been talking mostly about models based on magma ocean as a starting point. But why don't we just look at the oldest rocks on Earth to answer these questions about the early Earth, like we did on the moon? Well, there's not much left of the Earth's surface from that time. These are the two best examples, and almost the only examples we have of the Hadean, of things from prior to 4 billion years ago. The oldest known intact rock on Earth is the Acasta gneiss, discovered by my friend and mentor Sam Bowering in northern Canada, and it dates to 4.03 billion years. And the oldest known individual mineral grains are the zircons from the Jack Hills of Western Australia. There are 10 or 12 other places around the Earth where Hadean zircons, tiny crystals I'll talk about more, are found, but none are as abundant or old or as useful in understanding the geologic past as these Jack Hill zircons. Zircons, by the way, are the natural version of the late night television manufactured diamond replacement that's called cubic zirconia. So we're going to stick to the natural samples here, but that's actually what zircon is. It's the natural example of cubic zirconia. So we have scant direct evidence from our Hadean Earth of what it was actually like there. I want to just take a tiny moment before we go on to talk about the Jack Hill zircons, and let me say a little bit about Sam Bowering, the discoverer of the Acasta gneiss. Here's a picture of a piece of Acasta gneiss that I happen to own, and a Canadian coin for scale. Sam was a professor at MIT, and he was on my PhD thesis committee and my colleague at MIT, and he and I did field work in Siberia together, and he was a great friend, and he passed away last year. We miss him very much. He was one of the world's great geochronologists, figuring out the ages of rocks, the dates that rocks formed in the past. So a little tribute to Sam. Now, those Australian zircons. Here is a photograph of the sedimentary rocks of the Jack Hills of Western Australia. The ancient rocks in this photo contain within them zircon grains, these little crystals that are far older than the rocks themselves. Those rocks formed at about 3.6 billion years ago. So they're pretty old, but they gathered up, they were sedimentary rocks, and they contain much older individual crystals that weathered out of even older rocks. Within just 100 meters of this site, more than 95% of the zircons older than 4 billion years have been found. So this is a very special place on Earth, these Jack Hill zircons. All right, public service announcement on dating ancient zircons. Let's talk about the precise dates of these tiny zircon crystals and how they're determined, because it's very, very important for the story. So first, geologists since the 1950s have been using the uranium-lead decay systems for determining the ages of ancient rocks. It's the same way that calcium aluminum inclusions are dated. Beautifully, there are two such systems. Uranium-238 decays to lead-206, and uranium-235 decays to lead-207. And they have different half-lives, different amounts of time that it takes half of the uranium to decay to lead. They can both be used, and then the scientists can see whether they're in agreement as a kind of an internal check on the process. In its simplest sense, we imagine each mineral crystal as an isolated capsule ever since its formation. Count the number of uranium atoms in each one, and count the number of lead atoms, and then you can calculate how long the uranium has been decaying into lead. Now, it turns out that zircons, and here's a little outline of a zircon, have some special properties. One amazing thing about zircon is that it's incredibly tough. It doesn't break down easily with water and heat, and it's resistant to atoms diffusing in or out. It's almost the perfect isolated capsule of a mineral. The mineral zircon is made of zirconium, silicon, and oxygen. But when it crystallizes, it allows uranium into the crystal structure. But crucially, it excludes almost all of the lead. This is critical since another kind of crystal would allow lead also into its crystal structure, and there would be common lead incorporated into the crystal right at the beginning before its own uranium begins to decay. And that additional lead would make it look like the uranium had been decaying for much longer because of the excess lead. After one half-life, half the uranium would have decayed into lead. Time goes on. Eventually, a geologist comes along and collects this crystal and measures the uranium and lead contents, and then can calculate how many half-lives have passed. This system can be both extremely accurate and extremely precise, with errors significantly less than 1% for the best labs. It's an amazing thing to do. Here is a compilation of the ages of about 251 Jack Hill zircons. Time is on the horizontal axis, running the opposite way from my other timelines, unfortunately. The oldest are on the right. Even in this sample, and there are literally thousands more analyzed since this paper, thousands more crystals, there are quite a number of zircons between 4.3 and 4.4 billion years. That's just 100 million years after the moon forming impact. Now, what can we learn from these old crystals? Another public service announcement: oxygen isotopes in geologic sleuthing. So how do we use oxygen and in deciphering the geologic past? Oxygen comes in 3 isotopes, that is 3 weights. Oxygen 16 makes up most of the oxygen on Earth, about 99.76%. Oxygen 18 makes up just 0.2% of oxygen on Earth. And oxygen 17, which makes up a minuscule 0.04%, I'm not even going to mention it any further today. The Earth's average oxygen isotopic makeup, the one that I just recited, is measured in the oxygen making up the water in our well-mixed oceans. That's our reservoir. But physical processes change these typical ratios of isotopes in particular reservoirs of water. Because water molecules containing the lighter isotope of oxygen are slightly more likely to evaporate, so clouds contain slightly less heavy oxygen in them. So a little bit more of oxygen 16, a little bit less of oxygen 18. On the other hand, the weathering of rocks on the surface makes clays and other sediments that are high in oxygen 18 because the water that first binds to the rock to form new minerals is heavier water. Okay, think about that heavy oxygen wet sediment. That's what people think these zircons originated from. Almost all the Hadean zircons have elevated oxygen 18, indicating they formed, get this, they formed from a magma that was the result of melting rocks that had been altered by interacting with surface water. This indicates two things. One, there was enough groundwater on Earth to weather existing surface rocks, which were then buried and melted and crystallized into a rock that included the zircons. Main point, there was surface water. Because the oxygen isotopic ratios in zircons are indistinguishable from the range of later zircons from igneous processes, they demonstrate from an oxygen isotope perspective that no fundamental planetary scale change in magmatic processes is recorded in zircons from at least 4.3 billion to 2.5 billion from very, very early. Earth processes have been the same. So we had surface water very early and the processes more or less stayed the same. So here are some of these very early Hadean zircons. Note that the white scale bars next to each zircon, each is 100 microns long or 1/10 of a millimeter. They are tiny. Each has its age in millions of years just under each scale bar. And at the bottommost number is the excess of oxygen 18 in parts per million. All numbers over 5 of that oxygen 18 number indicate that these rocks have too much oxygen 18 to have just come from the regular mantle reservoir and they melted from an water-altered surface rock. A further line of evidence for a cool, wet, early Earth comes from titanium measured in these zircons. How much titanium is allowed into zircons as they crystallize is dependent upon its temperature. And on average, these zircons formed at about 680 degrees. This temperature fits very closely the final crystallization temperature of a wet granite. These zircons, as you now know, are an incredible resource for understanding our early Earth. The teams working on these zircons have created an almost industrial process for extracting and rapidly dating the crystals, and they passed by a long way 100,000 zircons processed. Let's think for a moment about what else is going on the Earth during and after magma ocean cooling. One of the big things is impacts, and in fact, the late heavy bombardment, which also happened on the Earth. In this study, Simone Marchi created simulations of the likely number and size of impacts into the Earth between 4.5 and 3.5 billion years ago, based upon all the impact information we have from the moon and also the distribution of sizes in the asteroid belt. Here's one of the simulations. The colors of craters indicate their age, as shown in the little bar. At the top left, the Earth is covered with impacts from 4.5 to 4.4 billion years old. The magma ocean is long solidified and the surface has cooled to allow surface water. These impacts seem to have interrupted the climate relatively little. By 4.1, the top right, only a small portion of the older dark red crust is now visible. Most of it has been overprinted by yellow and orange craters that date from 4.1 to 4.4 billion years ago. The big impacts of the late heavy bombardment show up as pale blue and green in the 3.8 billion year old image on the bottom left. And then impacts tail off, and only a few are recorded up to 3.5. So as significant as impact craters may have been on the early Earth, the presence of water breaking down and weathering away rocks may be the biggest reason we have so few ancient rocks today. Another may be the advent of plate tectonics, and we'll talk about that in a later lecture. So finally, over these 5 lectures, we've built up enough history and knowledge to make a really detailed timeline. I think this is one of the most amazing compilations of knowledge in science. Look at all we have learned about what our early solar system was like and when and how planets were built. Starting up at the top in purple, from planetesimals to planets, you can see core formation and planetesimals within the first million years, really, after the calcium aluminum inclusions, and then instabilities and pebble accretion create planetary embryos, and the dust and gas disk dissipates. It's gone. Notice the bottom scale of time from 4.567.3, the earliest calcium aluminum inclusion, only up a little past 4.3. So this is only about half of the Hadean. Next down is Mars. We haven't talked about Mars, but let me mention here that Mars appears to be one of those earliest little planetary embryos. It was fully formed not later than 10 million years, maybe 5 million years after the beginning of the solar system. And from Martian meteorites, we actually have a very early individual mineral found on Mars at about 4.49. Now, next down is the moon and the Earth. In that gray vertical bar, that's approximately the time of the moon forming impact. It lines up with those dark gray core formations of the moon. Then the anorthosites, that flotation lid on the moon, remelted by tidal heating, continuing to be formed for perhaps 200 billion years. And then the creep in blue, that last dregs of the magma ocean. So we know the magma ocean on the moon took 100 to 200 million years to solidify. But down on the Earth, the magma ocean solidifies in just 5 million years. There's no flotation lid on the Earth. The Earth has too much pressure, it's too big, and too much water. And in tens of millions of years, the Earth is cooled to clement surface conditions. And those terrestrial zircon minerals showing that there was water date all the way back to 4.4. So the moon is still solidifying, and on the Earth, there's water. I think it's amazing. So here's the wrap up. First, here's the time period shown on the last slide. Just that little blue part is what we were just looking at. Amazing how much detail we have. And here's the story of the Earth from 4.5 to 3.8. At around 4.5 billion years ago, the Earth experienced the moon-forming giant impact, and it melted into a magma ocean. Very little material exists from the pre-4.0 billion-year-old Earth surface. Thus, the Jack Hill zircons are key evidence for conditions. The zircons and models for magma ocean solidification both show the Earth was cool and clement before 4.4 billion years, despite the fact that there was a high impactor flux right up through the late heavy bombardment. And that is the early Earth. Thank you so much.